All right, here we go, guys. We are starting section 6.5. 6.5 is going to bring all of the other trigonometric functions graphs in. Yay, I'm sure you're all excited. So we're going to have tangent, cotangent, secant, and cosecant graphs, all right? I hope to get, oh, Michael, where did I put them? I hope to get all of them covered, although I think that's very, very optimistic of me. So we'll see how far we get, how many we can get graphed. If I don't get them all graphed, I'm not assigning homework yet. I'll wait till Monday to assign homework, all right? All right, so here we go. So if we're going to graph the tangent function, right? Remember, tangent, by definition, is the sine over the cosine. So literally, to make his ratios, you can take any y-coordinate off of the unit circle and put it over the x-coordinate, okay? Now, you'll notice, I don't mean to be a little bit of a spoiler, but the period of sine and cosine, the amount of inputs it takes to create one cycle or one wave, is longer than it is for tangent. Tangent actually starts repeating itself faster. It doesn't take as many inputs. So the period for tangent, and you're going to see it, it's actually pi radians. It only takes us pi radians to create one cycle or one period of tangent. So guys, if I take the period and I divide it into those like 4 sub-intervals, it means we'll actually be counting by pi's over 4, not pi's over 2. So we're going to do 1 pi over 4, 2 pi's over 4 actually reduces to pi over 2, and then you just count it. 1 pi over 4, 2 pi over 4, 3 pi over 4. So everybody do that. Label your x-axis by increments of pi over 4. So now, here are your quadrant 1 angles, here are your quadrant 2 angles, your quadrant 3, and your quadrant 4, and so on, right? We have an extra angle in the middle of a quadrant. When we graph sine and cosine, we literally just used our quadrantals. All right, so let's start at 0. So if I took the tangent of 0 radians, well, guys, go to 0 radians. It's right here. Throw the y-coordinate over the x-coordinate. 0 over 1 is 0. Okay, now we go to pi over 4. Guys, pi over 4, 180 divided by 4, it's 45. That's a 45-degree angle. So in your 45-degree angle, in your right triangle, O over A, your tangent is 1. So pi over 4 is 1. We're in quadrant 1. All tangent ratios are positive in quadrant 1, so that's 1. Okay, then we get to pi over 2, which is right here. The tangent of pi over 2, 1 over 0, guys, that's undefined. That's actually an angle that's not in his domain. So it literally produces an undefined output. So what actually happens there, because it's undefined, it's actually going to act as a vertical asymptote. The graph will never exist when x is pi over 2. It doesn't create a defined output. All right, then we go to 3 pi over 4. Guys, 3 pi over 4 is a 45-degree angle that landed in quadrant 2. So now the tangent of 45 is 1, but since it's in quadrant 2, all students, a y-coordinate over an x-coordinate, that would be a positive y over a negative x. So that would be a negative 1. It's a negative 1 this time. All right, and then we go to pi. You plug in pi, as at pi radians, 0 over negative 1, that's 0. All right, 5 pi over 4. Guys, 5 pi over 4 is right here. This is 4 pi's over 4, so here's your 5th one. It's the tangent of a 45-degree angle, but it put you in quadrant 3. What is the tangent of a 45? It's 1, and then because it's in quadrant 3, all students take, tangent ratios are positive for angles in quadrant 3. So now it's positive 1. All right, and then 3 pi over 2, what's a little high? Looking for it. the same. 3 pi over 2 is right here. It's your third 90-degree angle. Y over x is 0. Sorry, undefined. That's negative 1 over 0. That's undefined. That's another angle that is not in his domain. So it creates a vertical asymptote. So we've actually just seen our first complete cycle, but we'll come back. All right, now let's go to 7 pi over 4. 7 pi over 4 is your 45-degree angle, but it landed in quadrant 4, so the ratio is definitely 1. All students take calculus. The tangent ratio is negative for angles in quadrant 4, so it's negative 1. All right, 2 pi, guys, we're back to where we started. That's 2 pi radians right there. Y over x is 0. 9 pi over 4, your ninth 45-degree angle is in quadrant 1. Guys, your eighth 45-degree angle made 2 pi. Your ninth one is in quadrant 1. So the tangent of a 45 is 1. The ratio of all tangent angles is positive in quadrant 1. All right, 5 pi over 2, guys, that's your fifth 90th degree angle. 1, 2, 3, 4, 5. You're back where pi over 2 was. So you throw a y over an x, it's undefined. That's another angle that's not in his domain. All right, let's go back this way and create the other cycles. So guys, negative pi over 4, that's a 45-degree angle that landed in quadrant 4. So the ratio is 1. The ratio is negative because it's in quadrant 4. Negative pi over 2 is right there. Throw a y over an x, that's undefined. Negative 3 pi over 4 is in quadrant 3. Tangent of a 45 is 1. It's positive in quadrant 3. Negative pi is right there in the same spot pi landed. Y over x is 0. Negative 5 pi over 4 lands right here because this would be negative 4 pi's over 4. Your negative fifth one is in quadrant 2. The tangent of a 45-degree angle is 1. The tangent ratio is negative for angles in quadrant 2. And then last, negative 3 pi over 2 lands right up here in the same spot as pi over 2. Y over an x is undefined. Actually, I don't have that one in the chart, do I? Oh, guys, call me out. I missed a box. Okay, so here it is. So you have all of these broken curves, if you will. This does not make one smooth, continuous curve. It makes a lot of repeated curves. So if you think from a left to right standpoint, your asymptotes are like magnets. Your graph is drawn to them. So from left to right, I'm going to go from this dot to this dot to this dot, and I'm going to be drawn towards that asymptote. Then I'm going to go from right to left. I'll go from this dot to this dot to this dot and be drawn to that asymptote. So it looks like this. That is what your tangent curve looks like. And then it's just repeated over and over and over again. All right. So guys, you can see if you look at one cycle lives in between each pair of asymptotes. So this is one cycle. It went from negative pi over 2 to positive pi over 2. Guys, that's 90 and 90. That's 180. That's pi radians. It's pi radians that lives on each period, right? Then I went from pi over 2 to 3 pi over 2. That's pi over 2 to 3 pi over 2. That's pi radians. That's 180 degrees. That's what lives on each cycle of the tangent function. All right? All right, perfect. So let's see what our domain, all of our properties of this function is now that we see what his graph is doing. All right, the domain. Well, guys, what angles are you allowed to plug in? Obviously, there's lots of bad angles. So, and first of all, I want to mark this. The first cycle that we're going to call is going to be from negative pi over 2 to pi over 2. So this first cycle doesn't just start at 0 and go. Our first cycle, our first period is right here. All right, one cycle, one period, which is pi radians long. It goes from negative pi over 2 to pi over 2. Sorry, I wanted to mark that. All right, our domain. We have lots of angles that we don't want x to be. The first bad guy going right was pi over 2, and then 3 pi over 2, and then 5 pi over 2. So odd integer multiples of pi over 2 are bad guys. So we're going to say x cannot be pi over 2 plus or minus, because it could be positive or negative from there. Every pi radians creates another bad angle. So times pi k. X cannot be those. They are not in his domain. If you get there, they create an asymptote. All right, I already told you the period is pi radians. It only takes pi inputs to create one period or one cycle of the tangent function. The range. Well, guys, look at each curve. This curve is shooting down to negative infinity. This curve is shooting up to positive infinity. Your range is all real numbers. Think about it. O over A, it could be big number over small number. It could be small number over big number. The tangent ratio has no limit. It goes from positive infinity to negative infinity. All real numbers. Because it goes to infinity and negative infinity, to find an amplitude, which would be half the distance between the highest and lowest point, well, in reality, there is no high or low point. It's going to the infinities. So we say that the amplitude is like non-applicable, NA. We don't talk about amplitude as far as the tangent function is concerned, because he's going off to the infinities. All right, the x-intercepts. Guys, he has an x-intercept at 0, at pi, at 2 pi. The next one will be at 3 pi, because it's just going to repeat over and over and over again. So we could say integer multiples of pi creates an x-intercept, right? So we'll just say x equals, the first one is at 0, plus or minus, the next one's at pi, times k revolutions. 1 revolution would be 1 pi. 2 revolutions would be 2 pi, and so on. All right, the y-intercept is definitely at 0. If you remember our even and odd, this one has pi over 4, 1, and it also has negative pi over 4, negative 1. For each xy that lives on the graph, the opposite of x, the opposite of y lives on the graph. This is an odd function, and it has symmetry to the origin. Remember, only the cosine was the even function. All your other trig functions are odd. And that goes for their reciprocals as well. All right, VAs, guys, we got countless, infinitely many vertical asymptotes. I got 1 at pi over 2, at 3 pi over 2, at 5 pi over 2. Every time you get to an x value that wasn't in the domain, it's going to create a vertical asymptote. So there's infinitely many of them. They are all at odd integer multiples of pi over 2. But we'll just say this, x cannot be, or I should say x is, because now we're calling it the asymptote. X is pi over 2 plus pi times k revolutions. So the VAs will be at x equals pi over 2 plus or minus pi times k revolutions. Okay, now your subintervals and your key points. This should help when you have to transform the functions, but it's a little bit different in the sense that, remember, this first cycle didn't start at 0. So our subintervals are a little bit different, and we didn't count by pi's over 2. We counted by pi's over 4. So your first subinterval is from negative pi over 2 to negative pi over 4. Your next one is from negative pi over 4 to 0, and then 0 to pi over 4, and then pi over 4 to pi over 2. Those are the 4 subintervals that live on one or the first cycle of the tangent function. All right, so we go from negative pi over 2 to pi over 4 is our first subinterval. We go from negative pi over 4 to 0. We go from 0 to positive pi over 4. And then we go from pi over 4 to pi over 2. All right. Negative pi over 2 to pi over 4, negative pi over 4 to 0, 0 to pi over 4, and pi over 4 to pi over 2. It's these intervals right here, the 4 subsections of the first cycle. All right, and then your 5 key points that you could use to create that first tangent function, if you ever had to transform it. First point, guys, it's not really a point, but we're going to call it one. We're going to say negative pi over 2, undefined. That's your asymptote. So negative pi over 2 went in, and an undefined ratio came out. That's going to be our first point, our first asymptote, we'll say. All right, then we're going to say negative pi over 4, negative 1. Then we're going to say 0, 0. Then we're going to say pi over 4, 1 is our next key point that creates the first curve. And then we'll say pi over 2 undefined. So we can use them as our starting point to create transformations. All right, how do we feel with the tangent function? Okay? All right, let's do cotangent. Now, cotangent, guys, it's his reciprocals. So if you start thinking about what it looks like when you start reciprocating all of these ratios, well, technically the reciprocals of negative ones and ones, they shouldn't change. But the reciprocal of 0 is undefined. So all of his intercepts become vertical asymptotes on cotangent. Anything that is undefined, when you reciprocate undefined, it comes 0. So now all of his undefineds, his VAs, become x-intercepts. And it'll literally shift the curves. You'll see.
I just need bottom to stay. That's the 5 defaults.
They're going to be on the filled in ones.
Okay. Thank you.
All right, let's look at cotangent. So again, same information we can use over here, but remember, cotangent is the reciprocal, so now it's cosine over sine. So it's an x-coordinate over a y-coordinate now when you create those ratios. All right, here we go. Same thing. I'm going to be a little bit of a spoiler. It also has a period of pi radians that it takes to create one curve. If I cut that into 4 subintervals like the 4 quadrants did, we'll be counting by pi's over 4 again. So can everybody get your x-axis ready? Count by 1 pi over 4, 2 pi over 4, 3 pi over 4, and so on. All right, here we go. If we plug in 0, it's the cotangent at 0. Well, guys, at 0 radians, x over y is undefined. So it starts right at an asymptote, which is nice because it means his first cycle will start at 0. All right, pi over 4. Guys, the tangent of pi over 4 is 1. You reciprocate 1, it's still 1. We're in quadrant 1, so it's positive. It's positive 1. Pi over 2, x over y is 0. 3 pi over 4, guys, the cotangent of pi over 4 is 1. We're in quadrant 2, so now it's negative. All students, only sine gets you a positive ratio. All right, pi at pi radians, x over y, is that over 0? It's undefined. So guys, you've already seen, there's your first cycle of cotangent. From 0 to pi, it takes pi radians, and now the curve is going from left to right like that. So why don't we just use our repeating this? So the next one's going to be 1. Our next one's going to be 0. Our next one's going to be negative 1. All right, the next one will be undefined. All right, then we're going to be back up at 1, then at 0, then at negative 1. I know it stopped, but just to continue it, and then it'll be undefined again. Okay, if we go this way, guys, now we're next to the asymptote. So now it'll be negative 1, 0, 1, undefined. All right. All right, and then we're back here again. It'll be at negative 1, 0, and 1, and undefined. Okay, so now cotangent, if you think about it at the first cycle from 0 to pi, From right to left, it's going to go from this dot to this dot to this dot, and then follow that asymptote. From right to left, it's going dot to dot to dot, and then follow that asymptote. Right? So if you think about it, the tangent function was increasing from left to right. The cotangent is decreasing from left to right. All right. All right, here we go. Domain. What angles can we plug in? Well, guys, we got infinitely many bad ones, right? The first one was 0. The next one was pi. The next one was 2 pi. So integer multiples of pi are no good. So we're going to say x cannot be. I always say 0 and then plus or minus pi radians away is the next one times k revolutions. So again, integer multiples of pi are bad guys. Yes?
Is that equal or is that?
Oh, cannot be. Oh, God. We're good. All right. Period is pi. It only takes pi radians. So, guys, from 0 to pi, that's our first cycle. That's our first period. All right, the range. Same thing. Guys, look at your curves. They're all going to the infinities. It's going from negative infinity to positive infinity. So that means your ratio for cotangent can be anything. There's no ratio it can't spit out. All right, again, the amplitude will be non-applicable in the sense that we're going to the infinities, so how could there be half the distance between the highest and lowest point? All right, the x-intercepts. Guys, we got a lot of them. Our first one was at pi over 2, and then 3 pi over 2, and then 5 pi over 2. So odd integer multiples of pi over 2. So we're going to say x equals pi over 2 plus or minus, they're all pi radians away from each other, times k. The y-intercept, guys, there is none. It's an undefined x value that goes in to create an undefined ratio, so there's no y-intercept. It's none, it's undefined. The cotangent, just like his reciprocal, is an odd function with symmetry to the origin. For every point xy that lives on his graph, so does the opposite of x the opposite of y. Go ahead, Michael.
Before the x equals 0 plus or minus pi k, what is it? Is that just the arrow?
X equals?
The does not equal.
Oh, this is just my arrow from the curve and then my asymptote. Sorry, yeah, that doesn't mean anything.
I thought this was y1.
Yeah, it's just an arrow. With symmetry to the origin. Our VAs are at all of the x values that we weren't allowed to plug in. So now at x equals 0 plus pi times k, those are all of our VAs. All right, and then again, our 4 main subintervals on that first cycle. We're going to go from 0 to pi over 4, pi over 4 to pi over 2, pi over 2 to 3 pi over 2, 3 pi over 4, and then 3 pi over 4 to pi. Those are our 4 subintervals that we use. Okay, and then our key points, the key points that will allow us to create the first cycle of cotangent is going to be 0 undefined. That creates our VA. Pi over 4, 1. Pi over 2, 0. 3 pi over 4, negative 1. And then pi undefined. Creates another asymptote. Okay? All right, guys, I know I don't get far. There's so much information. And again, if they ask you to transform it, you got to know at least how the original one behaves to create that transformation. Do you guys graph these in Algebra 2? You've never seen the graphs then?
You didn't even get past basics of Patella.
Oh, Okay. Oh, then I don't feel like I'm like making you sit through something you've definitely seen before. All right, perfect. All right, so guys, I'm not gonna get to the secant and the cosecant, but guys, they're really cool in the sense that they're the reciprocal of cosine and sine. And those are hopefully the two trig functions whose graphs you can recreate the fastest. So if you think about how this is gonna go, if you picture your sine wave, right? Hopefully everybody can graph that. If you picture each part of the sine wave, if you reciprocate it, guys, if this is, let's say, 1/2, what's the reciprocal of 1/2? It's 2, right? This was 1, what's the reciprocal of 1? 1. If this was 1/2, what's the reciprocal of 1/2? It just flips each one of these curves up, and you're gonna get a bunch of parabola up. Take this, right? If all of these reciprocate, now it's going to create a parabola down. So it's just a big cycle of parabola up, parabola down, parabola up, parabola down. I call it parabolas. It's not a parabola, but it looks like one. All right. So they're actually extremely easy to create their graphs, but I'm still not going to be able to do that until Monday, which is good news, which means no homework over the weekend. Hopefully I'll graph the last two trig functions and I'll be able to give you your first, really it's more informational homework questions, not really too much math. And then on Tuesday, we can start the transformations of these functions, okay? All right, and then guys, just for a heads up next week, this is the last section we're covering, and then we're going to move to chapter 7, which is going to involve inverse trig functions, trig equations. It's really important for calculus. So I'd like to think we'll end next week with a quiz of some kind, but because it'll be rushed, it'll either be a study plan with almost no mastery points just so you have something to look at it, or I may not even give you a study plan this time, all right, just because I don't know how time will work. And prom is Friday, so I really don't want to quiz on next Friday. I'd rather quiz Thursday before prom if we can, so we'll see how that goes. But just know that this is the last section once we finally finish it, and then we'll go from there with some type of hopefully quiz, and then we're into chapter 7. All right, let me just double check the attendance.